every electron in your body, every electron on Earth, every electron in every star in the entire observable universe, they all have exact same charge, the exact same mass, and the exact same spin. They are perfectly, impossibly identical. And in 1940, a physicist named John Wheeler picked up the phone and called his student with an explanation so wild it sounds like a joke. Feynman, he said, I know why all electrons have same charge and why same mass. Why? Because they are all the same electron. It's not just that electrons are similar. In physics, two electrons are not merely identical to tell apart, they are indistinguishable. This isn't a limitation of our instruments, it's a property of reality itself. If you swap two electrons in a quantum system, the mathematics doesn't change at all, not even a little. The equations produce exact same result. This is a cornerstone of quantum mechanics, something called exchange symmetry. It means that the universe doesn't label electrons. It doesn't tag them. It doesn't give them serial numbers. Two electrons are not two things that happen to look alike. They are two instances of same underlying thing. Let this sink in. In every other domain of reality, objects have individuality. Two coins might look identical, but one could be minted in Denver and other one in Philadelphia. Two raindrops might be the same size, but they fell from different clouds. Individuality is everywhere, except here. At the deepest level of matter, individuality vanishes. Every electron is every other electron. This fact, the complete absence of identity at the fundamental level, is not a footnote. It's one of the deepest properties of the universe. And it's the key to a story that starts with a phone call in Princeton in the spring of 1940. John Wheeler was one of the most imaginative physicists of the 20th century. He named black holes, he coined the term quantum foam. He worked with other greats like Niels Bohr on nuclear fission and Einstein on general relativity. But in 1940, he was a young professor at Princeton, and one of his graduate students was a brash, brilliant kid named Richard Feynman. One day, Feynman would later recall this in his Nobel Prize lecture 25 years later. Wheeler called him up at the graduate college, and he said something that sounded like it couldn't possibly be serious. Feynman, I know why all electrons have same charge and the same mass. Why? Because they are all the same electron. Now, this sounds insane, and Wheeler knew it sounded insane. But he wasn't joking. He had been thinking about something, a mathematical observation buried inside the new quantum theories that was so strange, so elegant, that it almost forced this conclusion. Here is what Wheeler had noticed. In the Dirac equation, the equation that describes how electrons behave in relativistic quantum world, there is a mathematical possibility that had been puzzling physicists for years. The equation predicted that an electron could have a twin, a particle with exact same mass but opposite charge. This twin was called the positron, the antiparticle of electron, and it was discovered experimentally just few years earlier in 1932 by Carl Anderson. But Wheeler looked at this positron from a different angle. In the mathematics of quantum electrodynamics, a positron could be described not as a separate particle, but as an electron moving backward through time. Think about what this means. Not a new particle, not mirror image, the same particle, the very same electron just traveling in the opposite direction along with the arrow of time. Forward, it's an electron. Backward, it's a positron. One entity, two faces. Wheeler looked at this idea and pushed it to its extreme. If a positron is just an electron going backward in time, then what does full life story of an electron look like when you draw it on a space-time diagram? In physics, the path of a particle traces through space-time is called world line. For a normal electron, it's just a straight line moving forward in time. But what Wheeler imagined, a single world line that zigzags. It goes forward for a while, that's an electron, Then it turns around and goes backward. That's a positron. Then it turns forward again. That's electron. Backward, another positron. Forward, backward. Over the entire history of the universe, from the Big Bang to whatever end it awaits, this single word line would trace out an incomprehensibly tangled knot, a knot that passes through every moment of cosmic time over and over and over. Now, take a slice through space-time at any particular moment, say right now, this second. That slice would interact word line at an enormous number of points. Every single interaction is an electron that exists right now. Every point where the line is moving backward through the slice is a positron that exists right now. One line, one entity. But from our perspective, stuck in a single moment, unable to see the full knot, it looks like 10 to the power of 80 separate particles. It looks like a universe overflowing with electrons. But underneath is just one electron weaving its way through all of time. Wheeler told Feynman this idea with excitement of someone who had just uncovered secret architecture of reality. But Feynman, ever the pragmatist, didn't buy the whole thing. He didn't take the one electron part as a serious physical claim. Feynman took Wheeler's insight about backward in time word line and built it into the most powerful tool in quantum mechanics, the Feynman diagram. In a Feynman diagram, the annihilation of an electron and a positron isn't two particles destroying each other, it's one electron continuing its journey, but turning around in time. The creation of electron-positron pair isn't two particles being born from nothing. It's the same electron making a U-turn. Now let this sink in. The most widely used visual language in all particle physics, the diagram that appears on every textbook, every lecture slide, every physics paper, has its origin in a phone call about the idea that there might be just one electron, only one electron in the universe. Wheeler's wild hypothesis didn't become accepted physics, but the mathematical insight it revealed, that antiparticles could be understood as a particle moving backward in time, became a permanent foundational part of how we understand quantum world. Sometimes the most important ideas don't just come from careful incremental research, they come from a phone call, from someone who looked at a paradox and followed it all the way to its extreme, even when the extreme sounded absurd. So why don't physicists believe the one electron universe? Why did even Feynman, the man who stole the core insight, dismiss the one electron part? There are two crushing objections. First, the numbers don't work. If every positron is the same electron going backward in time, then the number of electrons and the number of positrons in the universe should be roughly equal. Every forward section of the word line produces one electron. Every backward section produces one positron. The knot should have roughly as many forward segments as backward segments. But our universe has vastly more electrons than positrons. The matter-antimatter asymmetry, the fact that we live in a universe dominated by matter, is one of the deepest unsolved problems in physics, and it directly contradicts Wheeler's idea. You cannot have an electron zigzagging through time and produce a universe that has billions of electrons but almost no positrons. Wheeler had thought about this. He had a workaround. He speculated that the missing positrons might be hidden inside protons, that protons somehow contained positrons that we couldn't see. But this was never verified. It was a guess patched onto a guess. Second, the identity problem. Quantum field theory gives us different explanation for why all electrons are identical, and it doesn't require single time-traveling particle. In quantum field theory, QFT, electrons aren't little individual objects. They are excitation of a single field, the electron field, that fills all of space-time. Think of it like a pond. Every ripple on the pond looks the same because the ripple is made of same water, shaped by same physics. Electrons are ripples on the same electron field. They are identical because they are all manifestations of same underlying field, not because they are all the same ripple traveling back and forth. This is the modern understanding, and it's elegant in its own way. But it's very different kind of elegance than Wheeler's. Now here's what makes this story worth telling. Even though one electron universe is almost certainly not how reality works, Wheeler's idea was wrong about the mechanism, but it was right about the mystery it pointed to. The mystery of identical particles is real. The fact that every electron is indistinguishable from every other electron is not a trivial observation. It's a profound clue about the structure of reality. Wheeler looked at that clue and said, maybe they are not identical copies. Maybe there is only one. And that leap, that willingness to follow a mathematical possibility to its most extreme, counterintuitive, reality-breaking conclusion is exactly the kind of thinking that drives physics forward. Even the ideas that fail to carry truth in them. Wheeler's one-electron universe failed as a hypothesis, but the insight it contained, that antiparticles are connected to particles through structure of time itself, succeeded. It became the backbone of Feynman's work. It became the part of standard model. It is woven into the equation that describes how quantum world actually works. The universe may not have only one electron, but the idea that it might, and the reasoning that led Wheeler to that idea, and the mathematics that Feynman extracted from it, exchanged our understanding from what an electron is, what a positron is, and what time itself might mean at quantum scale. In his 1965 Nobel Prize acceptance speech, Feynman told the story of that phone call. He stood on a stage in Stockholm, in the front of world's most distinguished scientists. The phone call happened in the spring of 1940. The insight it sparked, the array of time might be reversible for fundamental particles, helped build the most successful theory in the history of physics. Quantum dynamics, the theory that predicts the behavior of light and matter with an accuracy of 10 decimal places. 25 years after the phone call, Feynman stood in Stockholm and acknowledged that it all started with Wheeler's impossible idea. Not the idea itself, but the insight hidden inside it. Sometimes the universe whispers a secret that sounds too strange to be true. And even when the secret isn't true, the way it challenges your thinking, the way it forces you to reimagine what's possible, leads you to something that is. If this journey through one electron universe left you wondering about the deeper structure of reality, subscribe for more explorations into the strange rules that govern our cosmos. And let us know in the comments, what other mind-bending idea would you like us to unravel next? Thanks for watching.